In this video, we discuss the equilibrium between aldehydes and ketones and their hydrates, hemiacetals, and acetals. So by the end of this lecture, you should be able to say, I can manipulate the position of an equilibrium between aldehydes and ketones and acetals or ketals. Explain why a Dean-Stark trap is needed for acetal formation. Draw a mechanism for base-catalyzed and for acid-catalyzed acetal formation. Use aldehydes and ketones in multi-step syntheses of target molecules containing alcohols and acetals. You'll practice that during discussion section. And use acetals and ketals as protective groups in multi-step syntheses. Additions of oxygen nucleophiles to carbonyls are reversible reactions when in the presence of a catalytic amount of acid or base. The catalyst serves to lower the activation barrier for the reaction. Since the reaction is reversible, you might be wondering how we can get the product we want. We need to use Le Chatelier's principle to guide our thinking. If the acetal is the desired product, then we can either increase the concentration of one of the starting materials, remove one of the products, or add heat. To favor the ketone, we can add water, or remove product ketone or the byproduct ethanol. In the reaction above, we have a volatile alcohol as our nucleophile, so we would probably want to use ethanol as our solvent, so it would be in a very large excess, and that would help to drive the equilibrium toward the acetal there. In cases where your alcohol is not the solvent, but instead is actually some alcohol that you might care about, you need a different solution. And so there we're going to look toward removing water, and we can do that by using something called a Dean-Stark trap. So the way this process works is by taking advantage of an azeotrope. And so an azeotrope is a liquid mixture where the boiling point is different than that of its components, and importantly is lower than the components. With non-volatile alcohols, we usually make an acetal in a mixture of benzene and the alcohol and the aldehyde or ketone. So that'll be stirring here in your heating mantle. We heat that to reflux. So the vapor is going to be coming up this tube and falling back down. It'll eventually reach up to the condenser up here, and then when it drips from there, it actually drips into this side arm. And at this point, water and benzene will cool, and once cooled, they'll separate. And so the water that you're trying to get rid of in your flask, or from the reaction, is going to collect over here. And then as the reaction's proceeding, if you have a large amount of water being produced that you need to get rid of, then you can actually turn the stopcock here and drain the water and encourage more of this vapor to come over. In a base-catalyzed reaction, weak nucleophiles, such as water or alcohols, can be activated by deprotonation. So this forms a small amount of a more basic nucleophile, which can then add to the carbonyl. So if we go ahead and add hydroxide to the carbonyl, we then push up the electrons. This happens exactly like our carbanion nucleophiles to form a tetrahedral intermediate, as we did in that reaction. And now this oxygen anion is going to undergo deprotonation from water. And the product of that step is going to be actually the final product in this case, formalin. This is a very special name only for formyl-derived hydrates. So overall, this type of structure where we have kind of two alcohols coming from one carbon is called a hydrate, but this particular one made from formaldehyde is called formalin. In this step, when we did the deprotonation, we generated a new hydroxide anion, and this hydroxide anion will then go on to react with the next formaldehyde starting material. So it's important here to draw that because that's regenerating the catalyst. So formalin is a cool special case because unlike almost every other aldehyde or ketone, the formalin is actually the favored product in this equilibrium. So we'll take a look at that mechanism one more time, but this time in the context of a ketone. So we have a strong nucleophile, so we can just directly add that. And that's going to form this tetrahedral intermediate again. Now we do our deprotonation, and we form the hydrate and regenerate our catalytic hydroxide. In this reaction, we have methoxide as our nucleophile. This adds the same way. This time we're going to deprotonate methanol. And we're going to form our hemiacetal and regenerate our catalytic methoxide. So now we're going to look at the acid-catalyzed mechanism. In an acid-catalyzed reaction, weak nucleophiles can be activated by protonating the carbonyl. This forms a small amount of the activated carbonyl, which is more electrophilic than a regular carbonyl. The weak nucleophile can then add to this activated carbonyl. In this reaction, we have catalytic toluene sulfonic acid and water. So the first thing we need to do is protonate water to generate H3O+. Now we can use the basic lone pair on the carbonyl to deprotonate hydronium, and we form the activated carbonyl. So let's take a second to look at the resonance forms of this activated carbonyl intermediate. And we can compare those with the resonance forms of the starting material itself. So what we've done when we activated this carbonyl is essentially we made this resonance structure become a more dominant part of the overall molecular structure than this one had been for this ketone. Getting back to our reaction, in this step we kicked out water when we did this deprotonation. So we're going to go ahead and write in that water to balance our equation. And now the water is going to be our nucleophile. So it's your choice whether you add that to the major or the minor resonance structure. Most often you don't end up drawing this resonance structure, and so what you would do at this step is have water attack and push up the electrons here to the carbonyl. So when we do that step, we get to our next tetrahedral intermediate, and now this time, instead of needing to adjust the positive or the negative charge by protonating, we need to get back to a neutral compound here by deprotonating. The most basic thing in our reaction is actually the water molecule, and so we'll use water to deprotonate, and importantly, that's going to form our final product, the hydrate, and regenerate our acid catalyst. Next, we'll look at acid-catalyzed acetal formation. So this mechanism is a little more complex. First, we have to make the hemiacetal, and then we proceed from there to make the acetal. In the book, they separate this into two mechanisms, but in reality, you can't just stop at the hemiacetal in an acid-catalyzed mechanism, so that's why I'm doing them all together here. So first, we need to, just like we did with water, we need to protonate methanol with our tosic acid. This will form the protonated methanol, which we call a lyonium ion. And that's a term that just means a protonated solvent molecule. So it could be, any other solvent. It doesn't have to be methanol. And it would still be called a lyonium ion. So next we're going to take our basic lone pair from our carbonyl, and we're going to activate the carbonyl. So that leads to this intermediate here, the activated carbonyl, and produces the methanol. Methanol can then attack that carbonyl, and now we need to adjust our protons. Since methanol is our solvent, there's plenty of it around, so we can use methanol to deprotonate the tetrahedral intermediate. That leads to the hemiacetal shown here. In addition, it forms an equivalent of the lyonium ion, and so now we can actually protonate either one of these oxygens. If we protonate this oxygen here on the methoxy group, then we're going to head back to this intermediate. So for the sake of going forward, we're going to draw the protonation of this oxygen here. So now what we've done is we've activated this OH group for to make it into a good leaving group. So now we're going to kick out our good leaving group. And when we do that, the lone pair on our methoxy substituent will actually assist in that process by forming a pi bond. So that'll make a stabilized intermediate. Once again, methanol can add to this. This is also an activated carbonyl intermediate. And in the final step, methanol will deprotonate this to give the desired acetal and reform the catalytic lyonium ion. So now on your own, you can pause the video or try it after you're done with your just-in-time questions, but draw the mechanism for essentially the reverse reaction. We need to use different reaction conditions here, so we're going to use toluene sulfonic acid in water this time because we want to drive the equilibrium toward the ketone. So an exciting application of acetals is that they can be used as protecting groups, and acetals are used to protect both carbonyls and alcohols. So we'll show you these one at a time. Here we have a case where, let's say what we would like to do is a hydroboration of this olefin to form a primary alcohol here. Unfortunately, that desired reaction is not going to work. And that's because what will happen instead is you'll actually get reduction of the ketone as well. And so the product would actually be the diol. So it would have a secondary alcohol and the primary alcohol you were trying to make. So what we can do is use an acetal to protect our carbonyl and prevent it from undergoing hydroboration. So in the protection step, we're going to react our ketone with a diol, or you could use methanol and form a dimethyl acetal. In this case, we're going to make a cyclic acetal, and we're going to do that using 1,2 ethane diol here, which is also called ethylene glycol. So the acetal is not going to react with hydroboration conditions. So we can treat that compound with the borane, followed by oxidation with hydrogen peroxide in the presence of sodium hydroxide and water, and that is going to give us our desired primary alcohol. Now that we have the alcohol we need, we want to get our ketone back, and so what we want to do is take this back off, and we can do that by treating with tosic acid and water again. That's going to do the reversal of the acetal formation and give us our product ketone. So essentially, the protecting group functions like a raincoat. You know, when you go outside and it's raining, you don't want to just have your regular clothes, so you put your raincoat on, you go wherever you're going, you take your raincoat off, and there's your normal dry clothes again. So in this case, the ketone would be your dry clothes, and the acetal would be the raincoat. So now we'll do the mechanism for this reaction. We again start by doing the deprotonation of our acid. Then, because we're in acidic conditions, and now we have a positive charge here, we're going to do our deprotonation to activate our carbonyl. Next, our nucleophile is going to attack the activated carbonyl. And now we're going to adjust our protons. So we need to make this one neutral. And we're going to activate our alcohol for becoming a leaving group. Our lone pair is going to help us kick out water. And now here's the part that you guys will probably find a little bit tricky. We're actually going to do a reaction intramolecularly. So if we count from our pendant oxygen here, 1, 2, 3, 4, 5, we can see that if our oxygen were to attack the carbonyl, it would make a 5-membered ring. Making a 5-membered ring is favorable from an entropy standpoint. So now we can deprotonate to get to our final compound, and we've regenerated our catalytic species. In the next example, we'll look at protection of an alcohol. So in this desired reaction, what we want to do is add an ethyl group to this carbonyl to get a tertiary alcohol. Unfortunately, this is going to lead to no reaction at all because the ethyl minus is going to just deprotonate this hydroxide. That's going to sit there as the magnesium salt of that alkoxide until you add H3O+, at which point it'll be protonated again and you'll be exactly where you started. So what we want to do is prevent the deprotonation of our alcohol, and we're going to do that using a protecting group called the THP group, which stands for tetrahydropyran. So to do that, we're going to use an acetal as one of our reagents this time in the presence of acid. Okay, and this acid is going to help us kick out this group and form an oxocarbenium ion here. I'll show you this in a minute, and then that'll allow this oxygen to add to this carbon. So that'll put this group on here, the THP. The THP is stable to Grignard reagents. It's not going to react, and so now we can add our ethyl magnesium bromide. That's going to add as desired to the carbonyl only, and then we're going to do our aqueous workup, and that'll give us the tertiary alcohol. Finally, we'll remove the tetrahydropyran by doing the reverse reaction. So we'll treat with toluene sulfonic acid in water, and that'll do the deprotection reaction and give us the desired product. So as you can see, protecting groups can be really quite useful in a synthetic context in allowing us to do reactions that otherwise would not be possible. They do have a drawback though, which is that they automatically add 2 steps to a synthesis. So if it were possible to go from this starting material to this product, that would be 1 step. But this process we need to do now is actually 3 steps. So in this mechanism, we're going to start by protonating this oxygen. That serves to activate the leaving group, and so we can kick out our methanol. And that gives us this oxocarbenium ion. And here I've shown the resonance forms for that compound, so you can see that it's going to be electrophilic at carbon, not at oxygen, even though we usually draw the formal charge on oxygen to keep the pi bond there. So now we can go ahead and add our nucleophile, so the alcohol will attack. This is kind of a like a cyclic activated carbonyl here. Next, we're going to adjust to form a neutral compound, basically do a deprotonation. That's also going to regenerate our acid catalyst.